So we missed a day, but I think we're still okay. I think I had planned in a couple of even extra days for this spectroscopy section, so we get to the point where we can practice it some more. So let's quiet down, please. So just a reminder, I've been updating the sapling scores in Canvas and the iClicker scores. And again, if you've been doing these assignments and been here for clickers and your points aren't showing up, then it means that on sapling there's, on iClicker, on Reef, there's something wrong with your registration, right? Inputting the iClicker number, something like that. And with sapling, if you've been doing it, some of you I know put in your A number like it asks, but you didn't follow the rules on the format of the A number. All right, so if you're like, oh, I put it in, but my scores aren't showing up, you got to look at that. If you have a small A instead of a big A, then you got to change that. Or if you put a pound sign out in front, or some kind of thing that's not just capital A, then the number, then your scores aren't going to transfer. Okay? Yeah?
What's the practice clicker? Was that a permanent score?
The trial one? No, I'm going to take that out of there. Okay? So we have two, I think, just so far that'll be the permanent ones. Okay? All right, so try to just take care of that. Check it, take care of it now, if you can. All right, so this week we got homework 2 and quiz 2 going on. Here's next SIs this afternoon, or tonight. And we've got UTF office hours going as well. All right, so in this chapter we've talked about mass spectrometry, right? And we've talked about infrared spectroscopy. And we've seen a few examples, not a ton of examples so far, of both of those. Okay, let's stop talking, please. Still too much mumbling out there. So today what we're going to do is we're going to finish off this chapter. We're going to talk about the last technique, which is ultraviolet-visible spectroscopy. And I think, like I've mentioned before, this is not really a super powerful technique for structure determination, but it does have its applications, and so we should learn a little bit about it, all right? So if we get through that, which we may not, but if we do, we'll just start into an intro of Chapter 14, which is on NMR spectroscopy, and this is really the powerhouse of all of the structure determination methods, okay? Any questions? Business, anything? All right, let's do our clicker question then. All right, so UV-Visible Spectroscopy. All right, so this is just the last of our stuff down here bottom for this chapter. So remember what we talked about before, that ultraviolet visible spectroscopy is the right amount of energy to induce electronic transitions. So what we'll see is that it's going to be the right amount of energy to hop an electron from one orbital up to another orbital. And this actually takes quite a bit of energy. So ultraviolet and visible light is the highest energy light that we've used in any of our spectroscopy techniques. All right? And what it's good at is detecting conjugated pi systems. So what's a conjugated pi system?
Resonance.
It has resonance, right? But what do we need to have that? We have to have pi bonds that are linked together. Okay? Conjugate is when we have pi bonds next to each other. All right? So, just as we've kind of gone over this a few times, but we can treat light as a wave, right? And these are the equations right here that we've used, right? And we talked about that there's a direct correlation between the frequency and the energy. The higher frequency, the higher energy, right? And the wavelength over here, we have an inverse relationship, right? So the bigger the wavelength, the lower the energy, the shorter the wavelength, the higher the energy. So which one of these two waves, the bottom one or the top, would be higher energy? The bottom one, right? So this would be higher energy down here. right? Because it has a higher frequency, okay? All right, so visible light, so this is ultraviolet visible, right? The ultraviolet range is usually, so here, let's do it up here. UV is usually, we do this in wavelength, right? So each technique we use whatever they traditionally use, right? In IR, we use these reciprocal centimeters. In UV, we use wavelength. So the UV light is usually between about 200 nanometers and about 400. All right? Below 200, essentially that would get into what we call the near, the outside of the ultraviolet range, the high energy end of the ultraviolet range. And right, the electromagnetic spectrum is continuous going down that way. But most of the instruments that we use, the UV visible spectrophotometers they're called, go down to 200. Okay, so if the wavelength of light that's absorbed is below 200, we can't observe that. All right? And then visible light is usually starting above that, is from about 400 nanometers up to maybe 750 or something like that. Okay? Light in its own right, each of the different colors of the visible spectrum come from different wavelengths, right? So we usually think of, here's kind of the spectrum here, on this side down here is kind of the blue and purple. These are the shorter wavelengths, so this is higher energy. And red, orange, red, this side is longer wavelength, lower energy. Lower. And here's some of the ranges. And you don't have to memorize any of these things. But for blue light, it's down lower, red is up higher, this kind of thing. Remember that what we see as white light, a light bulb shines out white light or something like that, is a combination of all those wavelengths. So white light has all the colors in it, right? And in fact, when we see a color, what we're seeing is having some wavelength of light being removed, and we're seeing what's left over. Okay? So we can use this kind of color wheel over here. And what happens is if we absorb one wavelength, we see the complementary color. Okay, so for example, if we see something that's over here that's red, it means that it's absorbing something over here in the green. Okay, so we observe the remaining wavelengths as the complementary color. All right, so here's just some examples of some natural molecules. So, colored compounds are used as pigments and dyes and things like that. Here's a common one that maybe everybody has eaten before. So this is beta-carotene. So it gives the orange color in carrots, for example. It's in almost all plant leaves and things like that as well. Here's another compound, this quercetin. It comes from saffron, right? If you had Indian food or something like that. And let's just compare these two, right? So these are long conjugated pi systems, right? Lots of double bonds in a row. And so let's count how many double bonds we have and compare these two, compare their colors and relate those two. So, okay, so up here, right, if we start with this carboxylic acid as this pi bond, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 pi bonds. 9 pi bonds. Okay, and we see here this color here is supposed to be what color it looks like. So that's kind of in the yellow or orange color, right? And so if it's yellow or orange, it might be over here somewhere. That means it's absorbing over here, maybe at 420 or something. Okay? So then let's look at beta carotene. How many pi bonds does it have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 pi bonds. Okay? The more pi bonds, the longer the wavelength that's absorbed. The more conjugation, the longer the wavelength. All right, so beta carotene is really orange, almost red. And let's say that so let's put it over here somewhere. Right? And so that means it's absorbing down here at like 480. Right? So the more wavelength, the more pi bonds, it's absorbing the longer wavelength. All right, so this is a real qualitative thing here. So these are just some natural ones. This one up here, indigo, right, is used like in denim, stuff like that, blue color. This carminic acid over there, it's produced by an insect. I know I used to, when I was in grad school, I think maybe I told you, I worked on insects, and I went on some trips to Florida to collect insects, and you'd find these bugs like on the palmetto, on these palm plants. They'd be all covered with like some kind of, looked like silk or something, and you'd squish it, and it would be all red inside. And that was this pigment here, and it was used by like Native Americans and stuff to color things. Yeah, question?
We've got a spot on the middle where it jumps from 600 to 400 nanometers.
Mm-hmm.
So if we have it absorb on the opposite side, how do we know what wavelength it has?
Okay, so the question is, right here, right, we've made a wheel, right? So it's made it into a wheel, but in fact, it's not a cyclic thing, right? If we go below 400, then we're going down into the UV, right? And if we go above 800, we're going out of the top side we're going up into the infrared instead of the visible. So I think that's all just taken into account here. I don't know. I want to ask you to do this. This is a qualitative thing. Yeah, so they kind of bent it around. All right, so let's see what actually happens. So I mentioned that what's happening in ultraviolet and visible light is that light is absorbed and an electron is hopped from one orbital to another. So usually it gets bumped from what we call the HOMO, which is the highest occupied molecular orbital, okay, to the LUMO, which is the lowest unoccupied molecular orbital. Okay, so here's like all kinds of different combinations, possibilities. All right, so for example, here goes from a sigma bond, orbitals in a sigma bond, jumping all the way up to the sigma star. Right, so this is from the bonding to the anti-bonding, right, in a sigma bond, right? Remember those molecular orbitals. And we've got, various ones here, but the ones that really come out in the correct type of energy range for ultraviolet light are right here, okay? So really only the N, so N is non-bonding. So N to pi star, so pi star is the anti-bonding for the pi orbital. This is wrong. This should be pi to pi star, okay, have the right amount of energy. Okay. However, this n to pi star is kind of disfavored because if we think about, where we have non-bonding electrons, perhaps is say in a carbon-oxygen double bond, right? Here I'm going to draw this like this. All right, the pi bond, well, we actually want to have the pi star. Well, that doesn't matter. So the pi star, remember, is going to be one where the two p orbitals are aligned with opposite phases. Okay, so they would be like this. All right, so there's actually a node between those two, right? So then the non-bonding electrons, where are the non-bonding electrons relative to this on the oxygen? Where would they be oriented? So what kind of orbitals are the non-bonding electrons in for this oxygen? SP, remember we're looking at a pi bond here. sp2, right? So there's an sp2 orbital that's being used for the carbon-oxygen bond, and then there's two sp2 orbitals on this oxygen that are holding the two pairs of lone pairs or non-bonding electrons. So how would they be oriented relative to this pi star? They would be perpendicular, exactly right. So the pi star, do these in green, would be out this way and like this, right? So these would be the non-bonding electrons. So these are non-bonding, and they are in the sp2 hybridized orbitals. This one is the pi star. So we have the pi star going like this, and we have the non-bonding at 90-degree angle, right? So those orbitals cannot overlap very well at all. At 90 degrees, that almost means there's no overlap. So it's very difficult for the non-bonding electrons to get into the pi star, okay, because the orbitals don't overlap. All right, so this, in fact, this is disfavored because of poor orbital overlap, and sometimes it's disfavored. It can happen, but it's weak, and so that a lot of times they call it that it's actually, oops, I wrote that wrong. It's actually what's called a forbidden screw that up. Or forbidden electron transition. Okay? So pi to pi star is what we see the most. Okay? Pi to pi star. Now, if we have a single pi bond, all right, so a carbon-carbon pi bond, double bond, or carbon-oxygen pi bond, or a nitrogen-oxygen pi bond, they can absorb light, but look at the wavelengths of light that are absorbed, right? So what did I say? Are these wavelengths of light that we can observe in our experiment? No, they're too short of wavelength for us to absorb. Okay, so these wavelengths below, they correspond to an energy difference that's too great, right? It's out of the range of our instrumentation, of our typical instrumentation. There are instruments that can measure it in this range, but not the usual ultraviolet-visible spectrophotometer. Okay? So, what do? We can't look at single pi bonds, but we can look at conjugated systems. So, as we connect pi bonds together, the gap between what we call the HOMO, the highest occupied molecular orbital, to the LUMO, okay, this gap gets smaller and smaller. Okay? we could go through the whole analysis and draw out all the molecular orbital diagrams and all this stuff, but I think you guys probably don't want me to do that. So as we have more pi bonds, so more, not just any pi bonds, right? More conjugated pi bonds, the delta E is smaller. Okay? So it's only when we get at least to butadiene, so this is 2 double bonds, that we can even start to observe it. All right? And so here's 3 UV spectra, and these are more complicated than most of the ones that we'll observe. Usually what we'll see some examples, they're just like one big broad thing, or maybe a little shoulder on it or something. But these have more detail than usual. But the key thing to observe here is that here's our conjugated system. If we have N is 3, so we have 3 conjugated pi bonds. Okay? Then our absorbances, say here for the biggest peak. And if we add another pi bond, goes over here. If we add another pi bond, it's, I guess if we look at the same peak, it's over here. So it keeps jumping to a longer wavelength every time we add another pi bond. Okay? So this is just the general trend. Okay, so what do we get out of a spectrum? So here's another molecule and another UV spectrum. See, we see 2 peaks in this one. And what we see in the UV spectrum is on this side, we see absorbance. So this is how much light is absorbed. Remember in IR, we looked at percent transmittance, so that was the amount that's not absorbed. Okay? So in this case, we have peaks going up, and before we had peaks going down. And down here is wavelength in nanometers. All right, so the important things that we record if we're running a UV visible spectrum, one is called the lambda max. Okay, so these are essentially the top of the peaks, the maxima. All right, so in this spectrum, we have 2 lambda maxes. We have one right here at 255 nanometers, and we have another one right here at 395. Okay, so we'd have 2 lambda maxes. And then we also have what we call the molar absorptivity. Okay, and I think I'm going to show you what that is, if I remember correctly, on the next slide. Okay, so the molar absorptivity comes from this equation called the Beer-Lambert Law. Okay? Here it is. So, A is the absorbance. Okay, so this is what we read right off of the y-axis of our spectrum. Okay, this is how much light is absorbed. Okay, L in this case is the path length. So this is the size of our sample container, right? You could imagine that if you have a very large sample container, as the light shines through it, it's going to run into lots of molecules and a lot of light would be absorbed, right? If you have a very tiny sample container, the light would go through and it wouldn't hit as many molecules, and so it wouldn't absorb as much, right? So we've got to take into account the size of the sample container. So typically, usually, the sample containers, we call them a cuvette, are usually 1 centimeter, right? So that's easy, that just becomes a 1, okay? One thing that's important about the cuvette for doing ultraviolet light absorption, what do you think? What's one important thing about that? As far as materials and things like that. Right, it has to be transparent to the light we're absorbing. that we're measuring over, right? So you can't just use normal glass because it would absorb the ultraviolet light. So usually in the ultraviolet, these things are made out of quartz, right? And they're polished up really nice, okay? And they can't have little wavy things that would like bend and diffract the light off, right? It's got to be high precision quartz. Okay, and then C is the concentration, right? The higher the concentration, the more molecules there are to absorb light. And then E, or this epsilon right here, is what I mentioned on the last one, is in molar absorptivity. So the molar absorptivity is a constant for a given molecule. Okay? That tells us for a given molecule how strongly that molecule absorbs light, okay? So what we can do, we can use this equation in several ways. So if we have an unknown, right, and we're running the UV visible spectrum for the first time, and we want to report this, maybe in a journal article or something like that, then if we have this equation, we have like this, epsilon CL, right? We're going to measure this, right? We're going to know our path length, right? Or that's the concentration. We're going to know that because we're going to make up a solution and we're going to carefully measure the mass and dilute it to a known concentration. And the path length we also know, right? So from these, we can just rearrange this, and we can say epsilon equals A over CL, right? So we can calculate this value right here, right? So whenever we would report our data, so if we want to report this, we would usually we'd have some lambda max, and then in parentheses, we would list our epsilon. It might be 10,000 or 30,000 or something like that, okay? The other way that this Beer-Lambert law is commonly used is if we have a known compound that we know the epsilon value for already, right? And we can always measure the absorbance and we know the path length. If we have a solution of an unknown concentration, but we know the epsilon value, then we can calculate the concentration from the absorbance. So this is kind of more of like an analytical chemistry. We're going to measure concentrations, how much of this compound is present in your environmental sample or something like that. Right? So in this case, what we would do is we would calculate concentration from A over epsilon times L. Right? So here we could calculate concentration. Okay? So that's how it's often used. Right? So for more of an analytical technique. Everybody clear on that? Simple equation, right? All right, so let's just look at a couple more examples where we can actually get some structural information. All right? So we've already seen actually a couple of examples of this top one. So in general, as we increase the number of pi bonds, the wavelength of the absorbed light gets longer, right? Here's another example. If we have a ketone by itself, 195, we can't really observe that. It's out of our range. But if we have a pi bond, a carbon-carbon pi bond that's conjugated with that ketone, it goes up to 219. So now we can observe that. Okay? So this one is out of range. But this one we could observe. Right? So if you were looking at a bunch of data trying to come up with a structure, and one of the pieces of information that you were given was the results from the UV visible spectrum, and they said that the absorbance was at 220 nanometers, right? You would know that, okay, so if it was at, let's say, 220, right? These are not always exact, so it's about 219. And we had two choices. One was this versus this, right? We're trying to place the position of the pi bond. Which one of these would fit for the 220? The bottom one, right? Because from that result, we would know that this pi bond had to be conjugated to the ketone, right? It wouldn't fit for this one here. Okay? So this one would have to fit. Okay, another place that we can use this data is if we have groups that can function as acids or bases. All right? Then our absorption can be dependent upon pH. All right? So for example, if we have this molecule is phenol, okay, so it's an alcohol on a benzene ring. And if we add some base, maybe hydroxide to this, we raise the pH, then that phenol, the hydroxide can pull off that proton, and we get this one is called the phenolate anion. All right? So we've increased the amount of charge on that oxygen. All right? So what do you think this might do to the wavelength of the absorption, of the lambda max? No. So what happens is, so even in this case, oh, so somebody else want to guess now? So even this oxygen can donate electron density into the ring, right? And if we draw out that resonance structure, right, we put some plus here, minus here, but we notice that we've extended the pi system up to the oxygen, all right? But when we have this minus charge here, it can really do the same thing, but because it's donating more electron density, it actually shifts it to a longer wavelength, okay? So the lambda max for this phenolate anion is at 287 nanometers. Okay? These groups that are attached to the benzene ring are called an oxochrome. Oxochrome. So these are just groups that are attached to, this is the terminology I haven't even told you about yet. So the pi system that absorbs light is called a chromophore. Okay? And if we have a group that has non-bonding electrons like this attached to the chromophore, it's called an oxochrome, and it can shift the lambda max one way or the other. Okay? So what do you think here? So this compound is called aniline, right? So it's got an amine group on the benzene ring, right? This is its ammonium ion. Okay, the ammonium ion absorbs at 254 nanometers. So if we, like in the other one, if we add some base to this, we can deprotonate the ammonium ion to give this free amine. All right? So what do you think? Is the wavelength for aniline going to be longer or shorter than that of the ammonium ion? How many people think longer? Raise your hands. All right. How many people think shorter? Raise your hands. Nobody? Okay, so you guys were right? So in the ammonium ion, how many non-bonding electrons are on this nitrogen? None, right? What about when we get to this free amine over here? 2, right? It has a pair of non-bonding electrons. So in this case, we can have resonance like this. But for the ammonium ion, there's no resonance up to the nitrogen, right? So by having those non-bonding electrons, it's going to increase the pi system, the size of the pi system, and so it should shift the lambda max to a longer wavelength. So this is, in fact, at 280 nanometers. Okay? All right, so these are systems here that sometimes you could actually get some information. If you had an unknown and you ran the UV visible spectrum at 1 pH, and you change the pH and you see a change in the lambda max, then it indicates that you must have some acidic or basic group. All right? And this is what happens for things like pH indicators, right? So have you heard of phenolphthalein or some of these pH indicators which will change colors at a certain pH? And in every case, I think, they have some type of acid or base properties. So it either extends or shortens the pH when it gets protonated or deprotonated. And so those are how those work. Okay? All right, so the other types of applications for UV visible spectroscopy some of them are listed here, all right? So one thing we've already mentioned, that it provides some information about conjugated pi bonds, but really it gives us little structural information except for kind of those examples that I gave you at the end. All right, so one of the applications it's often used is as a method to detect different compounds. So have you guys done thin layer chromatography? So TLC. So oftentimes the thin layer chromatography plates have a fluorescent indicator in them, right? And so usually you hold a UV light over it and it glows back at you green because the light is going in and it's being given back off. But if you have a molecule on there on the TLC plate that absorbs UV light, then it essentially quenches the fluorescence. So it doesn't turn green anymore. It's more like pink or something like that. So you can hold up the UV light to those TLC plates and you can see where the compounds are. All right? So that's one way. Another way is it's oftentimes used as a way to measure kinetics, concentrations at times. So, for example, I don't know if Dr. Henke ever talked about this kind of thing, but in his lab, they work on enzymes that are called phosphatases. All right, and what they do is they cleave off phosphate groups off of molecules in biological systems. And in fact, putting on and taking off these phosphate groups on proteins can act as kind of like activity switches, right? So either you put on the phosphate and it turns on the enzyme, and you take it off, it turns it off, or vice versa, all right? So there's a real important control mechanism for enzymes in biological systems. So oftentimes, his group uses this molecule here. So O, and then it'll have like a phosphate group out here. And depending upon the pH, these OHs will be either protonated or deprotonated. Okay, so they'll do something like this, and then their enzyme, so their phosphatase, will cleave that off and give them this, plus they get, it's transferred to whatever, the phosphate over here. But this compound, because it has this phenolate anion and it has this nitro group over here that can further the conjugation. You guys remember what you guys do these kind of resonance. So here's a nitro group, right? And so we could go through and show how the non-bonding electrons here and the charge can go here, can go here, can go here, go all the way out here on the oxygen of the nitro group, so it extends the pi system. So this one absorbs UV light, but this one absorbs visible light. Okay, so the presence of the amount of this tells us how far the reaction has proceeded. So they can measure kinetics and things by using ultraviolet and visible light. Okay, so it's also a good method for quantification, like we said, with the Beer-Lambert Law, if you want to measure amounts, concentrations of known compounds. Chromatography, I don't know, have you guys heard of HPLC, so high performance liquid chromatography? So that's a common chromatography method used in labs, and it can have UV detectors. One thing that's important, if you are doing UV visible spectroscopy, we typically have to run this as a dilute solution, and when we look at that UV visible spectrum, the peaks have to be below 2 absorbance units. If it gets above 2, that Beer-Lambert law is no longer linear because sometimes the instrument doesn't function well above that. And you can get, it gets saturated and really throws it off. And the last thing is, of course, the solvent, whatever you're going to dissolve your solvent in, can't be absorbing light in that range either. So you have to have a solvent that doesn't absorb in the UV or visible range. Okay? So that is the end of UV-Vis. And we have chapter 13, and so tomorrow we're going to start in on chapter 14 is NMR spectroscopy.